thinking of it as a number line, 2, 1, 0, right? And negative 1/3. You don't have to put these numbers in between, but just realize it's a number line and all the numbers are happening. 0 is in between here. So if I want to know the sign here, I could plug in 0 for this equation. Okay, so plugging in 0 here goes away to 0. 0 minus, okay, that becomes 0 as well. 0 minus 0 minus 3 is negative 3. All I want you to realize is it's negative. So our sign here is minus. Then try and think of easy numbers that can go in. You could plot in 4 and find out what is that sign. Or try and think of it as really big numbers. If I put in 10, let's say, that would be 300, because 10 squared would be 100. So 300 minus 80 minus 3. That's definitely going to be positive, right? 300 minus 80, we haven't even gotten to 200 yet. Minus 3, we're still not at 200. It's very positive. So pick numbers that kind of indicate to you like an easier instinct. Negative 10 here, negative 10 would still be positive 100 times 3 is 300. Okay, well then that would be times negative 10 plus 80. Okay, we're getting even more positive. Minus 3, definitely still positive. These guys tend to alternate. They tend to alternate. Not always, and we don't need to memorize any more rules because we have enough in our brain, but they tend to alternate. Okay, we've just created our sign diagram. Now we're going to use our sign diagram to find the coordinates at these maxima and minima and then determine which one's a maximum and which one's a minimum. Which means I need to plug in these values into my original function. F of negative 1/3 equals. Go ahead and plug it into your calculator. Negative 1 divided by 3 cubed minus 4 times negative 1 divided by 3. Crazy number, crazy fraction. I'm going to do 3 sig figs, 12.5. F of 3, same thing. Coordinates. And then I just need to really quickly ask myself, is this a maximum or is it a minimum? So I look at the signs. Go ahead and tell me what this point is with the negative 1/3. Does that represent a maximum or a minimum? Because it's first increasing and then decreasing, it's a maximum. This guy, because it's decreasing first and then increasing, it's a minimum. Okay. Moving on. Really quickly, we're going to do something that I think is pretty cool, and hopefully a few of you think that is pretty cool as well, is we're going to prove that the x-coordinate of the vertex of any quadratic, no numbers, but it's okay, of any quadratic we could possibly think of, all of the quadratics will have an x-coordinate of a vertex of this, which we've learned. We learned it when we were talking about quadratic modeling. If we're talking about a vertex, that means your derivative, right? It's your maximum or your minimum, but we're saying derivative. More specifically, when your derivative is equal to 0. So what if I just first found the derivative? Can you find the derivative when there are no numbers? Absolutely. It's the same process. 2 times a. And then 2 minus 1 is just 1. Okay, so it's just x there. And you've just found the derivative of this guy. Plus b times x. Well, that would be 1 times b, which is b, and then x to the 1 minus 1, 0. It goes away, and we're just left with b. C is just a number, so it goes away. The derivative of it is 0. So we now have the derivative, and we say, okay, well, the vertex happens when the derivative is set equal to 0. And now I want to solve for x. Okay, well, I should subtract b from both sides. And then if you divide both sides by 2a, you get x equals negative b over 2a. You've been using calculus this whole time. A lot of students ask me, where do we use calculus? Where is calculus used in the world? There's a lot of things like formulas and things that you learn early on, and they're like, well, why is this the thing? Well, this is one way to show that the x value of your vertex is just finding the derivative of any quadratic and then setting it equal to 0 will give you that value. So I think it's cool. All right, absolute maximum or minimum. We've been talking about relative maximum and minimum this whole time, right? We've been talking about or local, as we call it. Local maximum or relative means that, okay, this is a maximum value, it's a turning point, but realize over here there are values that get much taller than that, right? So it's not really your absolute, it's not the maximum, right? The maximum would be wherever this line curve ends. This is not the minimum. The minimum, if we follow this curve down this way, is wherever this curve ends. So it's a localized maximum, a localized minimum saying, okay, well, in this world, that's a maximum. In this world, that's a minimum. So now we're going to talk about absolute maximums and minimums. There's kind of like two situations that we talk about in regards to that. The first one is that domain restrictions can first of all count as local maximums and minimums. And sometimes can be your absolute maximum. When you have a domain restriction, let's say for instance this, it's a parabola, but you have distinct endpoints. You have a minimum, but your endpoints then create this idea of a maximum, right? You have two different endpoints and one happens to be higher than the next, well then that would be your absolute maximum. But you have two relative maxima, and one minimum, which would be your absolute minimum. So you see that like now adding in this idea of a domain restriction, which is our next problem, could alter what is a local maximum or minimum, and it could also contribute to an absolute maximum or minimum. When we have multiple maxima or multiple minima, we need to check the y values to see which one is absolute. Which makes sense. You find local, okay, well, which one has a higher y value? That would be your absolute maximum.